Welcome back. Section 5.1 Areas between curves. In this section, we learn about computing areas between two curves. Consider the following shaded region bounded by the graphs of y equals fx, y equals gx, x equals a, and x equals b. All right. This is the curve y equals fx. This is the curve y equals gx. X equals a and x equals b are vertical lines. Okay, x coordinate fixed number, x coordinate another fixed number. These are vertical lines. So that is x equals a and that one is x equals b. You want to calculate the area between these curves. This curve, these lines. Okay, that's your shaded region. Now notice this shape is not a rectangle, it's not a circle. We don't have any fixed rules. So how do we find area between two curves? Well, we divide that region into strips, thin strips like these of equal width. So that is one strip. So you take this region, the entire region, and divide it into strips of equal width. All right. And now what? Each such strip can be approximated by a rectangle. Okay. I hope you are understanding. Now you see we are looking at an approximation. So I could choose some point here and find its corresponding height. Say I'm using the left end point, I could use this height here and this height here. That's corresponding to the left end point. Now if I use the right end point for the rectangle, then I will use the right height. Okay, and you get a rectangle. Either way, depending on the choice of your element in your subinterval, you can attach a height to the rectangle, and that height is the length. So width times this entire height. Okay. Now notice the word approximated. So you need to approximate with rectangles. So you will lose some area, you may gain some area depending on where you draw your heights of the rectangles. Okay. Now, so choose any sample point, xi star, any sample point. Corresponding to that, right, you have points on the curve y equals fx, y equals gx. On this curve, you have the point xi star, fxi star, yf, because that's the curve y equals fx. Likewise, on the curve y equals gx, y coordinate is g of xi star. So corresponding to that one point, you have a point on your curve, a point on that curve. Okay. Now, you can use height to be that given by that point. You see, xi star is any sample point. So for any sample point in your interval, you can come up with a rectangle. All right. So I better draw it straight. There you go. So that gives me my rectangle. Likewise below. And that seems to be fair enough, right? So that looks like a reasonable rectangle. You lose some, but you gain some, and so on. Okay. Now, so what is the height of this entire rectangle from top to bottom? Well, the height or the length of the rectangle is bigger height minus smaller height. Bigger height minus smaller height. The width of that rectangle, we call it delta xi. You see, width of the rectangle is what we call delta xi. So the area of that ith rectangle is delta x times length of the rectangle fxi star minus gxi star. You recognize this? This is exactly like, this is essentially the Riemann sum. Okay, we saw in our previous sections. So, assuming you have n such rectangles, we have an approximate area between the two curves given by the Riemann sum, summation of the areas of each of all the rectangles, summation delta x fxi star minus gxi star. So what is xi star? Xi star is any point in the interval for the ith rectangle. You will have many rectangles. For each rectangle, take a sample point, find the height for it on F, height for it in G, find the difference. That will be the height of the rectangle. Delta x is the width of each rectangle. So if you have forgotten what Riemann sum is, go back to videos on chapters 3 and 4 and you will see, you will recognize what this is about. So that this is an approximation. Now, when you let number of rectangles to infinity, when limit n approaching infinity, summation from I to n delta x fxi star minus gxi star. This limit is the actual area A of the region between the two curves. In the picture above, the area between the two curves can be viewed as the difference of area under the curve y equals fx and the curve y equals gx. You see, when fx is greater than or equal to gx, as in this picture, f is bigger equals g, it's above g. Well, you look for area under the curve of f, you look for area under the curve of g. The difference between the two is the actual area between the two. Notice, because g is below, this area, if you use integration, you're going to get negative. So the top area minus a negative area is basically the addition of the two areas. Okay, so don't let that negative sign bother you. So if my function f is greater equals g, then we get, using the fundamental theorem of calculus part 2, the area A of the region bounded by the curves y equals fx, y equals gx, x equals a and x equals b, where the continuous functions fg are such that fx is greater equals gx over the entire interval a to b. The area A is integral from a to b fx minus gx dx. So this is, if you have forgotten, my suggestion, recall the fundamental theorem of calculus. Recall the fundamental theorem of calculus part 2. And then you will recognize where this comes from. This limit A is actually integration. That's what the summation results into, integration. All right. So that's what gives me the area between two curves. All right. So now what happens if my curves intersect? Look, f is above g for a while, but here are regions where g is above f. So here the curves intersect, and over certain subintervals fx is greater equals gx, and over some other intervals gx is greater equals fx. What do we do then? Notice the meaning of absolute value fx minus gx. Absolute value fx minus gx is precisely fx minus gx if fx greater equals gx. All right. You see, if fx is greater equals gx, this difference is non-negative. So absolute value of non-negative is itself. On the other hand, if gx is greater equals fx, then this is the positive magnitude of this expression. Okay? So think about it, you realize whichever is bigger comes first. That's what absolute value gives you. So, whichever is bigger has to be written first. That's what gets you area between the two curves. Higher curve minus lower curve, that integration gives me area between these two. Higher minus lower. So, in other words, you can simply say area A of the region bounded by curves y equals fx and y equals gx between x equals a and x equals b, where function f and g are continuous over closed interval a b. So now I don't know which one is above which. So what do? I simply write absolute value fx minus gx. A is integral a to b absolute value fx minus gx dx. Okay. Now let's go to examples in our next video. Until then, bye.